Alright students, so for this project what we're going to need is we're going to need something, way to measure angles, and you're going to need something to launch. Now I figured one thing we might all have at home is like a rubber band or a hair tie. Alright, something elastic like that. And what we're going to do basically is I have an app on my phone called Angle Measure. There we go. And you can tilt it and it will tell you the amount of degrees you're at. So it's going to be very easy for us to measure the degrees. So if we want to launch something at a 12-degree angle, we can do that 19-degree angle, any angle we want. And then we're going to pull this back sort of consistently. We want a consistent length we're pulling it back to. So you sort of slide it there, get the angle, and then launch it off like that. Okay, so that's sort of the setup for this activity. Okay, so you'll need your phone. You will want an app called Angle Pro or some other app that will do that for you. The other. All right, students. So for this, we're going to be basically at the intersection of physics and trigonometry. We've done trigonometry. That's the sine, cosine, and tangent. That's triangle measurements. That's what trigonometry is. And physics involves all kinds of different phenomena. So for the physics part of this, we're going to be dealing with velocity, distance, and time. So you may remember the formula. Distance equals rate times time. So you could also say distance equals velocity times time. These are both the same. We're going to actually think about it as velocity because we're actually going to be doing the difference between them is velocity actually has a direction to it. Whereas rate's just sort of you're traveling at 30 miles an hour. We're going to be traveling at a certain miles an hour in a certain direction. Here's what I mean. We talked about shooting the rubber band off your iPhone and measuring the angle you were doing that at. So if we simplify that and draw that as a triangle diagram, so picture this is the rubber band that you stretched, okay, and you're doing it at some angle from horizontal, because here's the idea. If you did it horizontal, all your energy would be in the x direction. Or if you shot the rubber band straight up, all its energy or all its velocity would be in the y direction. Okay, so this part of it here represents the velocity, and the idea is part of the velocity is in the x direction, part of it is in the y direction, and the more you tilt it, you affect how much energy is going in each direction. All right, so if we went 100% straight up, all the energy would be going straight up and straight down, all in the y direction. If we went 100% horizontal, it would be strictly in the horizontal. So this x component is actually a component of velocity, so we call this Vx, the velocity, the x component of the velocity. And same thing here, we put Vy. So how are all these related? Well, that's trigonometry. This is a right triangle, and so we can say then that the relationship between the x and the velocity is this. The cosine of theta would be adjacent over hypotenuse. In the right triangle here, this is just an adjacent side, and this is just a hypotenuse. So the cosine would just be the ratio of Vx over V. So if we want to know how much of the actual momentum, or how much the velocity, how much the velocity is in the x direction, we could solve this by multiplying both sides by V, and you get that. Now, if that's not clear, let me show you right now. If you put a V on both sides, like that, voila, the V's cancel on this side, and you get V times cosine of x. Sorry, V times cosine of theta equals Vx. So this is how much of the velocity is in the x direction. So how far do we expect our rubber band to go? Well, if we plug it in here, we can say the distance would be equal to V times cosine theta times t. So instead of velocity times time, we have velocity times cosine. Whoops, I'm sorry. There you go. Now you can see it. Instead of velocity, d equals v times t, instead of velocity, we have just the velocity of the x direction, and it's that. Now, this may look bad, but take a look. You can easily measure the distance. We can measure the time, and we did the angle before we even launched it, so that shouldn't be too hard. So we should be able to find any one of these things. It's not easy to find the velocity, but we can easily measure distance with a ruler. You can measure the time it launched with a stopwatch or the stopwatch on your phone, and then we know the angle, so we plug in those numbers. So we have all the parts. You plug them in, you can find the velocity. If you know the velocity, you can plug in to find the other parts. All right, so we're going to try that right now. So here's our situation. You launch a rubber band at an angle of 19 degrees. It flies for 0.7 seconds and travels 25 feet. Find the velocity. All right. Now, if you're good with cranking out equations, you can go do that. I'm just going to redraw the diagram. I really like drawing, and I also really think it helps to have the diagram. So let's do that. So there's our diagram. Let's make sure we put everything in the right locations. This is 19 degrees. The velocity would be, we don't know. That's what we're searching for. And we knew it traveled 25 feet. So in our diagram, if this was 25 feet, it went something like that. But it started with that angle. So it does follow the shape of a parabola, but when it started with our diagram we're going to use as a triangle. So that's, triangle is representing what's in here. So 25 feet later it lands. And so again, we said distance equals velocity times time, except for we're only concerned with the velocity in the x direction. And again, what we solved that for, we said that was v times cosine, and I'll have 19 degrees here times t. Now, we also know the 0.7, so we can plug that in for t, and we know it went 25 feet. So as you plug in everything in here, there's less and less that's unknown. Now, we plugged in our 25 for d, our 0.7 for t. These are all just numbers. And cosine of 19 is just a number. We could look it up in the table, or we can look it on the internet. So on the calculator it says cosine of 19 is 0.98887. It's good to keep that much accuracy. It's also good to make sure important to make sure you're in degrees. It's critical to make sure you're in degrees, not radians for this one. Okay, so check that on your calculator. If you're using the internet calculator, do that. Now, in our equation, we also had to multiply that times 0.7, times 0.7, and that's our answer, 0.69209. We'll put 0.692. Okay, let's come back to here. So 0.692, that's what we had. 25 equals v times, all this was 0.692. That's what this whole thing is. And then to solve for v, divide both sides by 0.692. All right, so 25 divided by 0.692. So 25 divided by 0.692. So our velocity was actually about 36.12. Actually, I should round it out to 36.13. Okay, so let's take a look over here. Our velocity is about 36.13. So how does that gel with it? You're like, wait, that was 25. So most of our total velocity is about 36. Some of it's in the x direction, some of it's in the y direction, and we just found the x direction. That's how much velocity was, that's all total velocity, and if we plug that in again, we can find out the velocity in the x direction. Let's do that right now. The overall velocity was 36.12, and the x component of the velocity was just the v times cosine of 19. So take this, plug it in there, now you got the x component. And let's do that. Again, when you're doing the calculator, go ahead and if you have it in the calculator, keep all this accuracy and then round out off at the very end. It's a little bit better that way. All right, if we multiply it out, velocity in the x direction is 35.7. So pretty close to the actual overall velocity. Okay, so that is the x component, and again, if we did it exactly similarly, we could do it for the y component. The y component would just be, if we set up, this is opposite, that's hypotenuse. So we could say then sine of 19 degrees equals velocity in the y over that, or opposite over hypotenuse. And again, these are just numbers. It looks bad at first, but they're just numbers. 19, so you're either given the angle or you're given the velocity, and you solve for the other one. All right, we have all the numbers we need. We could plug in and solve that. That's how we're going to do it for our rubber band launching project. So you now know how to do all the math for the x component and y component. And what you're going to find is the more, if you're setting it up over and over and over again, take a look. The 19 is not going to change, so take a look at what changes for each one. You don't have to set up the same equation each time. I mean, what I mean is you can save yourself some time when you're setting up the equations. You'll see what I mean when you set up the spreadsheet and see the table for that. All right, everyone. Thank you for watching, and I'll check in with you next time.